Hi there, in this video I'm going to do a past exam question on differentiation. So let's take a look at this question. Question number 9. The curve C has equation y equals 12 square root of x minus x to the power 3 over 2 minus 10, where x is bigger than 0. In part A, use calculus to find the coordinates of the turning point on C. So let's think about the question. Let's go back to the paper and pen. Now, in order to work out the coordinates of the turning or stationary point, we need to use the condition that for any turning point, dy over dx is equal to 0. So dy over dx is equal to 0 means that the gradient of the tangent at that turning point is 0. So we need dy over dx for us to apply that condition. So instead of having root x, let me write root x as x to the power of half. So let me write y as 12x to the power of half minus x to the power of 3 over 2 minus 10. And let's differentiate this instead. So let's calculate dy over dx. To work out dy over dx, remember the idea, we multiply by the power and subtract 1 from the power. So when I differentiate 12x to the power of half, if I multiply by the power, half times 12 is 6. And then we subtract 1 from the power, half minus 1 is minus half. Let's go through the second term. When I differentiate minus x to the power 3 over 2, first multiply by the power, 3 over 2 times minus 1 is minus 3 over 2. And then subtract 1 from the power, 3 over 2 minus 1 is half. Now if you differentiate any constant, the answer is 0. So if we differentiate minus 10, it's 0. Now if you're unfamiliar with differentiation, I have created a video explaining the method and I'll provide a link to that video in the description below. This is a solution for dy over dx. But remember the condition for turning or stationary points. So for any turning point, the gradient of the tangent at that point, meaning dy over dx, is equal to 0. So let's equate dy over dx to 0. Let's calculate the x coordinates of the turning point. So here's dy over dx, so it's 6x to the minus half minus 3 over 2 x to the power of plus half. Let's equate that to 0. What we can do is, I don't like negative powers, negative half powers. Let's get rid of them. So let's multiply the entire equation by x to the power plus half. So let's get rid of that negative power. So if I multiply throughout by x to the power plus half, I'll get 6 minus 3 over 2. X to the power of half times another x to the power of half is going to be x to the power of 1. So when you multiply two terms of the same base, remember we add the powers, so half plus a half is 1. That is equal to 0 times x to the half is 0. So what I did over here is to get rid of that negative half power, multiply by x to the power of plus half. Now let's work out the x coordinates. So what we could do is we can rearrange. So if I bring this negative 3 over 2x to the right, I'll have plus 3 over 2x, that's equal to 6. And if I divide both sides by 3 over 2, x therefore is going to be 4. So this is the x coordinate of the turning point. Now to work out the y coordinate, the corresponding y coordinate, it's straightforward. Put the x coordinate into the equation of the curve for y. So let me put x equals 4 into the equation for y. So put x is equal to 4 into y. So let's do that to give us 12. So 12 into the square root x, which is replaced by 4, minus x, which is 4, to the power 3 over 2, minus the 10. So this is what we have for the moment. And if we simplify this, so let's do the calculation. Square root of 4 is 2. 2 times 12 is 24. 4 to the power 3 over 2, so that is 8. Minus the 10 at the end. And when I simplify further, 24 minus 8 minus 10, that is 6. So the corresponding y coordinate is 6. So therefore, the turning point will have coordinates. The x value is 4, that's the x coordinate of the turning point, corresponding y coordinate 6. So that completes part A of the problem. Let's go to part B. So in part B, what we need to calculate is d2y over dx squared. So we need to find d2y over dx squared. So let's go back to the paper and pen. Now to find d2y over dx squared, we need to differentiate dy over dx again, or in other words, we need to differentiate y 2 times. So since we have dy over dx, let's differentiate again. Let's work out d2y over dx squared. So let's copy the dy over dx solution. So on the reverse, here's part B. So for dy over dx, we had, so just to remind ourselves, 6x to the minus half minus 3 over 2 x to the power plus half. So 6x to the minus half minus 3 over 2 x to the power plus half. So that is what we have for dy over dx. And what we need to do is we need to differentiate again to calculate the second derivative, d2y over dx squared. So remember the idea of differentiation: multiply by the power, subtract 1 from the power. So if I multiply by the power, minus half times 6 is minus 3. And if I subtract 1 from the power, minus half minus 1 minus 3 over 2. Let's differentiate this term also. When I multiply by the power, half times minus 3 over 2 is minus 3 over 4. And if I subtract 1 from the power, half minus 1 is minus half. So that is what you should have for the second derivative. That's the solution for part B, d2y over dx squared. Now let's go back to the screenshot. So we have a further part. The last part, part C, is to state the nature of the turning point. So let's think about this problem. Let's go back to the paper and pen. Now to work out the nature of the turning point, there's a couple of ways that we can do that. One of the ways is by using the second derivative test. Now we have the second derivative, so let me copy that down. So d2 over dx squared, we know from part B we had minus 3x to the minus 3 over 2 minus 3 over 4 x to the minus half. So that was our solution coming from part B. Now the idea of the second derivative test is we first need to put the x coordinate of the turning point. So the x coordinate of the turning point was 4. We need to put 4 for x into d2y over dx squared. So when I do that, d2y over dx squared is going to be minus 3, x replaced by 4, so 4 to the minus 3 over 2, minus 3 over 4, x replaced by 4 to the power minus half. So first step is to put the x coordinate of the turning point into the second derivative. Now if we do this calculation, you should get an answer of minus 3 over 4. Now if the value of d2 over dx squared at the turning point is negative, so our value is negative, and if it is negative, that means that you have a maximum turning point. So since d2y over dx squared is less than 0, we have a local maximum or a maximum turning point. So therefore a local maximum point. Now, if you're unaware of the second derivative test, I have done a video explaining the test and I'll provide a link to that video in the description below. But let me remind you of the other two conditions. Supposing if you have d2y over dx squared being bigger than 0 at the turning point, in this instance you'll have a local minimum, so a local minimum turning point. And supposing d2y over dx squared is equal to 0, so the test in this case will be inconclusive. So the test will be inconclusive, and you also need to consider the gradient either side of the turning point. But once again, in the video that I'm linking below, I'll go through the tests in detail. So be sure to check out that video. So in regards to part C, we're finished. We have a local maximum turning point since d2 over dx squared is less than 0. And we also finished solving this question. So that sadly ends the video. I hope you found this video helpful. I hope you enjoyed the video. If you did enjoy the video, a like rating is very much appreciated. Do plenty of practice related problems and I hope to see you again. Thank you.